This is Mr. Lee's physics class. I'm Mr. Lee. In the previous videos, we have learned that the heat capacity of a body is the heat needed to raise its temperature by 1 degree Celsius. But this is not convenient as this depends on the mass of the body. Say, if 2 kg of aluminium needs 1,800 joule of heat to rise 1 degree Celsius, then 4 kg of aluminium would need double the heat, that is, 3,600 joule of heat to rise 1 degree Celsius. That is to say, the heat capacity for 2 kg of aluminium is 1,800 joule per degree Celsius, while the heat capacity for 4 kg of aluminium is 3,600 joule per degree Celsius. Indeed, with these data, eventually we can find the heat capacity for whatever mass of aluminium. But this is troublesome. Why not just have the heat capacity recorded for 1 kg of aluminium? This leads us to the concept of the specific heat capacity of a substance, usually denoted by the small letter c. It is the heat to be absorbed by specifically 1 kg of the substance for it to rise by 1 degree Celsius of temperature. In the example of aluminium just now, for 1 kg of it to rise 1 degree Celsius is of course half of this value for 2 kg of aluminium. That is, 900 joule of heat is needed for 1 kg of aluminium to rise 1 degree Celsius. So, the specific heat capacity of aluminium is 900 joule. But 900 joule per what? Of course per degree Celsius, as we are talking about raising 1 degree Celsius of temperature. But it's not just that. It's specifically for 1 kg of it, so we should have per kg here in the unit. So, the specific heat capacity small letter c of aluminium is 900 joule per kg per degree Celsius. From this, it's also obvious that the so-called specific heat capacity is just the per kg version of the heat capacity of a body. So, using the symbols we just introduced, dividing the heat capacity capital C by the mass m will give you the specific heat capacity small letter c. You should note that since the specific heat capacity is by definition for 1 kg of substance, it doesn't make sense to speak of things like the specific heat capacity for 4 kg of aluminium or 2 kg of aluminium. It's just for the substance aluminium as it is 900 joule per kg of aluminium per degree Celsius. In view of this, specific heat capacity is about the substance itself and not how many kg of the substance there is. For example, the specific heat capacity of the substance water is 4,200 joule per kg of water per degree Celsius. That of the substance water in solid state, that's ice, is 2,100 joule per kg of ice per degree Celsius. That of the substance iron is 450 joule per kg of iron per degree Celsius, etc. and etc. This is good because it means people can record the specific heat capacity of various substances in various days in a data table for people to look up. You may also give it a try. Just search specific heat capacity, silver, on the internet. You will get what to expect. Let's take water as an example. Suppose through an experiment, it is found that 63,000 joule of heat is needed to raise the temperature of 5 kg of water by 3 degrees Celsius. Then the specific heat capacity C of water, that is the heat to be absorbed by 1 kg of water to rise 1 degree Celsius, is then given by the heat absorbed, 63,000 joule, divided by the temperature rise 3 degrees Celsius. And up to here, this gives you how many joule of heat is needed to raise 1 degree Celsius, but for 5 kg of water. To further get the heat needed to rise 1 degree Celsius for only 1 kg of water, we should further divide this by its mass, 5 kg. Evaluating, the value is 4,200. Let's check whether the unit is correct. Joule divided by degree Celsius and then further divided by kg of course give you this, joule per kg per degree Celsius, which echoes what I mentioned a little earlier. Let's view from the unit once again the meaning of specific heat capacity of water in this example. It simply means that 4,200 joule of heat is needed for specifically 1 kg of the substance water to rise by 1 degree Celsius. Now, let's take a closer look at how we have obtained the specific heat capacity C. We found C by dividing the heat Q absorbed by its mass m, and then further by the temperature rise delta T. So this is the expression for the specific heat capacity C of a substance. Once again, their units are joule for heat Q, kg for mass m, degrees Celsius for delta T, and naturally that for the specific heat capacity C is joule per kg per degree Celsius. In practical applications, it's often more common and useful to remember this equation in its rearranged form. Q equals mc delta T. You should note that when we use this equation concerning the specific heat capacity C, the heat Q can be a heat absorbed and the corresponding delta T would then be a temperature rise. The heat Q can also be a heat released and then the associated delta T would represent a temperature drop. This is exactly like the situation of this expression with heat capacity we discussed before. The reasoning for this has been discussed in an earlier video and I'm not repeating it here. The important thing is, both of these two equations relate the heat Q absorbed or released by a body to its temperature rise or dropped delta T. With this, we can add a bit to the definition of the specific heat capacity. It can also be the heat released by 1 kg of a substance to drop 1 degree Celsius of temperature. Let's now work on a problem about specific heat capacity. Suppose now I have 180 grams of coffee at 20 degrees Celsius. Well, that's pretty bad. And so I want to reheat it with a typical microwave oven with a typical power of 800 watts. Assuming that the specific heat capacity of coffee is about the same as water, that is 4,200 joule per kg per degree Celsius, how long should I reheat the coffee if I want it served at 70 degrees Celsius? As I introduced in an earlier video, this falls under an important type of problems about heat. That something releases heat and something absorbs this amount of heat. I'm not repeating the exact logic here. In short, the general strategy is to equate the heat released to the heat absorbed. In our problem here, we have the heat released by the microwave oven being equal to the heat absorbed by the coffee. Next, to relate the heat Q released by a heating device to its power P, the equation to use is Q equals PT. And to relate the heat absorbed by the coffee to its corresponding temperature change, we use Q equals mc delta T. Then plugging in the appropriate values as shown, we have this. This change of temperature delta T comes from that it rises from 20 degrees Celsius to 70 degrees Celsius. Solving and manipulating the units correctly, we have T equals 47.25 seconds. So this is about how long I should heat my coffee. What if I forget to switch off the microwave oven until it's heated for 1 minute and 10 seconds? Again, the same logic. Set an equation for the heat released by the microwave oven being equal to that absorbed by the coffee. And again, heat released by the microwave oven is related to its known power through PT. And heat absorbed by the coffee is related to its temperature rise through mc delta T. And putting in the right values in SI units, we have this equation, and is solved to give delta T the temperature rise equals 74.1 degrees Celsius. Since the heating starts from 20 degrees Celsius, this would mean the final temperature TF equals 20 plus 74.1 degrees Celsius and equals 94.1 degrees Celsius. Well, too hot to be a cup of good coffee. But I want to remind you that these results are only theoretical. We got them by assuming that the energy released by the microwave oven is all absorbed by the coffee. That is to say, the cup does not absorb any heat and no heat is lost to the surrounding environment. But this is simply not true in reality. Can you imagine how these results would differ in reality? For this one, the time needed to heat up the coffee to 70 degrees Celsius. If some heat released is not absorbed by the coffee, we will have to wait longer for enough heat that is absorbed by the coffee to rise to 70 degrees Celsius. So, actually the microwave oven should be switched on for longer than 47.25 seconds. If you are to understand this from a mathematical point of view, the heat released besides being absorbed by the coffee is also lost. So, we add this term Q loss here. Then solving, time t equals 47.25 seconds plus an extra positive term, So the time to reheat the coffee is longer than 47.25 seconds in reality. What about this in reality? The final temperature is heated for 1 minute and 10 seconds of time. Try to analyze this the same way I've just done. Let's analyze several common situations without numeric calculations. Suppose we have two bodies X and Y, and X has a greater specific heat capacity than Y. Case 1. If they have the same mass m and have risen the same temperature, X would absorb more heat than Y does. You can feel Y easily. Trust me, pause for 20 seconds and think about it. Understanding this through an equation is equally easy. Since Q equals mc delta T, and now X and Y have the same mass m and the same temperature rise delta T, then the object with a greater specific heat capacity C must absorb more heat Q, and that's body X here. Case 2. If X and Y absorb the same amount of heat and result in the same temperature rise, what does it imply about their masses? For this one, it's not that easy to feel the conclusion. Then mathematics may be a more systematic tool. So again, Q equals mc delta T. To compare their masses, let's first make mass m the subject of this expression. Then we have this. For the same heat Q absorbed resulting in the same temperature rise delta T, the body with a greater specific heat capacity C must have a smaller mass m. So, having a greater specific heat capacity, body X must have a smaller mass than Y.